Hello, everyone. Welcome to the course on computer networks. In the last class, we introduced three common computer network architectures. In this class, we will discuss the necessity of layered architecture in computer networks. Computer networks are highly complex systems. As early as the design phase of ARPANET, the concept of layered design was proposed to tackle this complexity. Layering can break down large and complex problems into smaller, more manageable ones, which are easier to study and handle. Now, let's proceed in order from simple to complex to understand the main issues encountered in implementing computer networks and how to divide these issues into corresponding layers of the five-layer architecture for layered processing. Starting with the simplest case, where two computers are connected via a single link, we need to consider the following issues. The first issue is what transmission media to use. Various transmission media can be used for the transmission link, such as coaxial cable, twisted pair cable, fiber optic, and wireless space. The second issue is what physical interface should network devices, such as user hosts, switches, and routers use to connect to the transmission media. As shown in the figure, the RJ45 Ethernet interface commonly seen on computer motherboards. After determining the transmission media and physical interface, we also need to consider how are bits 0 and 1 represent in the signal, and then transmit them over the transmission media. For example, using such a digital baseband signal, a high level represents bit 1, and a low level represents bit 0. By solving these issues, two computers can transmit bits 0 and 1 through signals. We can categorize these issues into the physical layer. Please note, strictly speaking, the transmission media does not belong to the physical layer category. It is not included in the computer network architecture. Furthermore, the signals transmitted in computer networks are not the simple digital baseband signals we exemplify. We use this example to make it easier to understand. When learning the abstract concepts of computer network architecture, we don't want to introduce additional technical details that might hinder students' understanding. Practical computer networks are often composed of multiple interconnected computers. For example, hosts A, B, and C are interconnected via a bus, assuming we have solved the physical layer problem, meaning that hosts can transmit bits 0 and 1 through signals. Let's see what other issues need to be solved in such a bus network. Suppose host A wants to send data to host B. The signal representing the data will propagate to every host on the bus. Then the question arises, how does host B know that the data is intended for it from host A and accept the data? And how does host C know that the data is not meant for it and should be discarded? This naturally leads to the issue of how to identify hosts in the network, known as host addressing. You may have heard of MAC addresses hard-coded on network cards. They serve as the host address in the network. When a host sends data, it attaches the source and destination addresses to the data. When other hosts receive it, they decide whether to accept the data based on whether the destination address matches their own. Additionally, the source address allows identifying which host sent the data. This also raises another question. How does the destination host distinguish between addresses and data from a continuous stream of bits represented by signals, which leads to the need to solve the encapsulation format of data packets? Furthermore, for bus networks, there may be collisions when multiple hosts contend for the bus. For example, if the bus is idle at a certain moment, meaning no host is using it to send data, but a moment later, hosts A and C simultaneously use the bus to send data, this will inevitably result in signal collisions. Therefore, coordinating the contention for the bus among hosts is also a problem that must be solved. It should be noted that such bus networks have long been phased out, and what is commonly used now is switched Ethernet, where multiple hosts are interconnected by Ethernet switches. In switched Ethernet, multiple pairs of hosts can communicate simultaneously without collisions. So, how do Ethernet switches work? Specifically, it's based on the principle of self-learning and forwarding frames. For wired networks like switched Ethernet, data errors are rare, while for wireless networks, data errors are more common. This leads to the issue of how to detect errors in data during transmission, known as error detection. When errors are detected in data packets, should they be discarded immediately, or should the sender be asked to resend the packets with errors? This leads to the issue of how to handle transmission errors when they occur. According to application requirements, transmission services can be divided into reliable transmission services and unreliable transmission services. Let's consider another scenario. Host A continuously sends data to host B, but host B is busy processing many other tasks and cannot retrieve cached data in the input buffer in time. So, host B sends a notification to host A to stop sending, which leads to the issue of the receiver controlling the amount of data injected into the network by the sender, known as flow control. We can categorize these issues into the data link layer. By now, you may have realized that once we solve the issues faced by the physical layer and the data link layer respectively, data packets can be transmitted within a single network. Indeed, that's true. However, our network applications are often not limited to a single network. For example, the Internet, which we use almost every day, is composed of many interconnected networks and routers. Merely solving the issues of the physical layer and the data link layer is not sufficient for it to function properly. We can consider such a small interconnected network as a small part of the Internet. Let's see what are the main issues to consider in this small interconnected network. As shown in the figure, because the interconnected network is composed of multiple networks, interconnected by multiple routers, we also need to identify each network in the interconnected network, which leads to the issue of network and host addressing. I'm sure you've heard of IP addresses. For example, these are the IP addresses assigned to the interfaces of devices in network N1. Since hosts H1, H2, and router R1 are connected to interfaces in network N1, they are all in the same network. Therefore, their IP addresses have the same network number, which is 192.168.0 in this example, while their host numbers are different 1, 2, and 254 respectively to uniquely identify them within network N1. Similarly, we have assigned corresponding IP addresses to hosts H3, H4, and router R2 connected to network N2. Please note that the network number assigned to network N2 is 192.168.1, which is different from the network number 192.168.0 assigned to network N1 because they are different networks. Let's consider another issue. In an interconnected network, there are often multiple transmission paths between the source host and the destination host. Data packets from the source host to the destination host can take different paths, which leads to the issue of how routers forward data packets and make routing decisions. We can categorize these issues into the network layer. So far, if we solve the issues of the physical layer, the data link layer, and the network layer respectively, we can achieve the transmission of data packets between multiple networks. However, for computer network applications, there are still some important issues to consider. For example, suppose host H3 runs two network communication-related application processes. One is a browser process, and the other is a QQ process. In this scenario, a web server is running a web server process related to network communication, such as Nginx. When host H3 receives a data packet from the Nginx process in the web server, should it deliver the data packet to the browser process or the QQ process? Obviously, if the data packet contains flags related to the processes, host H3 can deliver the data packet to the corresponding application process based on the flags. This leads to the issue of how to identify application processes related to network communication, thus solving the problem of network communication between processes. For example, using port numbers to distinguish between different application processes. In previous classes, we mentioned that data packets are discarded by routers or user hosts due to errors, or normal data packets are actively discarded due to busy routers. These all fall under the category of transmission errors. So, how should transmission errors be handled when they occur? This is also an issue that needs to be solved. We can categorize these issues into the transport layer. So far, if we solve the issues of the physical layer, the data link layer, the network layer, and the transport layer respectively, we can achieve network communication between processes. Based on this, various application protocols can be developed and corresponding application programs can be written according to protocol standards to achieve specific network applications through interaction between application processes. For example, supporting the HTTP protocol for the World Wide Web, the SMTP protocol for email, and the FTP protocol for file transfer, among others. Additionally, when formulating application protocols, we also need to consider session management and data representation issues when application processes communicate over the network. We can categorize these issues into the application layer. So, We have categorized the main issues that need to be solved in implementing computer networks into the physical layer, the data link layer, the network layer, the transport layer, and the application layer, thus forming a 5-layer architecture. The physical layer solves the issue of how to represent bits 0 and 1 using signals. The data link layer solves the issue of transmitting data packets within a network or segment. The network layer solves the issue of transmitting data packets between multiple networks and routing. The transport layer solves the issue of network communication between processes. The application layer solves the issue of implementing specific network applications through the interaction of application processes. Now, I want you to think. If you were a programmer tasked with solving various software problems faced by computer networks, would you prefer to implement all these problems in one module, or divide them into different modules and implement them one by one? I believe you would choose the latter. This is the concept of high cohesion and low coupling in software engineering. This class ends here. Let's summarize the content of this class. Students, see you in the next class.